Okay, so that's the comparison theorem. Let's go through some examples on that. Okay, example number 1. Prove that the integral from 0 to infinity of e to the minus x squared dx is convergent. Okay, so we want to prove this. Now, this function, e to the minus x squared, it doesn't have a very nice antiderivative. So it's not easy to find the antiderivative of that. Okay, so not easy to find the antiderivative of e to the minus x squared. And so we can't do this directly. So instead, we're going to break this problem up into 2 parts. And then we're going to see that for the second part, we can replace this integral with an approximation, so a bound like this. So instead of having f of x, we're going to have something smaller, or some g of x and f of x that bound each other. And we're going to see that the one part converges. So the other part must also converge. Okay, in this way. Okay, so what we do is we split this integral up into 2 parts. So we have the integral from 0 to infinity of e to the minus x squared dx is equal to the integral from 0 to 1 of e to the minus x squared dx plus the integral from 1 to infinity of e to the minus x squared dx. Okay, so we split it up. So notice that this first part is just a normal definite integral. There's no asymptotes, there's no infinite domain. So we know that this first bit is going to be finite. So what we need to do is check this other bit over here. So this other part here, this has an upper bound of infinity. So we need to check if this is finite. Okay, so we want to check if this thing converges or not. So let's go back to our theorem here. So we look at this first bit that talks about convergence. Yeah, so what we do is we're trying to see if this function converges, the g of x. So what we need to do is find some upper bound f such that that integral converges. So if the upper bound function converges, then our original one will also converge. Okay, so we need to find what this f can be. Okay, so we have this bound from 1 to infinity. What kind of function is close to e to the minus x squared, but we know converges? Okay, that's going to be e to the minus x. Okay, it's similar, but we know that since x is greater than or equal to 1, we know that x squared is going to be greater than or equal to x. So minus x squared is less than or equal to minus x. So e to the minus x squared is less than or equal to e to the minus x. So on the left-hand side, we have our original function. And on the other side, we've got a new function that is an upper bound. Yeah, so for all x greater than or equal to 1, we have that this new function is bigger than our original function. So you see how it matches with our theorem here. We've got a new function f that's bigger than our original function. And if our new function converges, then our original function also converges. So we just need to show that the new function converges. So if the integral from 1 to infinity of e to the minus x dx converges, then the integral from 1 to infinity e to the minus x squared dx also converges. Yeah, and that's the key idea. We've replaced this more complicated integral, the e to the minus x squared, with a much simpler integral, e to the minus x. Okay, and that's easy to show convergence. So we just replace this with what we know. That's the limit as t goes to infinity, the integral from 1 to t, e to the minus x dx. That's going to be the limit as t goes to infinity of minus e to the minus x from 1 to t. That's going to be the limit as t goes to infinity of minus e to the minus t minus, well, minus and a minus, that's going to make it plus, e to the minus 1. And then as t goes to infinity, the first term goes to 0, and we're just left with e to the minus 1. But we're not really interested in what the value is. All we want to know is that this is less than infinity. So the solution is finite. The solution is finite. And so this integral converges. Which means our original integral converges. Okay, so since the simpler function converges, and the simpler function is an upper bound for our original function, so since that one converges, the original one also converges. Okay, so we can go back here and we know that the blue part is finite, the green part is also finite, so the whole thing is less than infinity, which means it converges. Okay. Okay, let's see if there's any questions. Okay, I've got a question here. So may you please go over the approach again? Okay, sure, we can do that. Okay, so let's just take a look at it again. Okay, so we need to show that the integral from 0 to infinity of e to the minus x squared dx converges. Okay, now this e to the minus x squared is something that we can't integrate directly. So we can't just find the antiderivative of this. So we can't find the antiderivative of e to the minus x squared. So instead, we find an upper bound, some function that's bigger than it. So we find an upper bound and show that it converges. So if the upper bound function converges, then our original function converges. Okay, so that's the idea here. We're trying to find an upper bound function that's a lot simpler compared to what we have at the beginning. So e to the minus x squared, that's pretty complicated. But if we can rewrite this as e to the minus x, okay, if we can show that that's an upper bound, then that's a lot better. So let's just look at what this graph looks like. Okay, so e to the minus x squared is going to look something like this. Okay, on the other hand, e to the minus x is going to look something like that. Okay, and then this crossover point here, let's say over there, that's going to be at 1. Okay, so why is it at 1? Because for 0 less than or equal to x less than or equal to 1, x squared is less than x. Okay, because we're dealing with fractions. If you square a fraction, it gets smaller. But for x greater than or equal to 1, x squared becomes bigger than x. Okay, so what we need to do is split this integral into 2 parts. One that's before 1 and the other that is after 1. Okay, because of this relationship here. Before 1, x squared is less than x. After 1, x squared is greater than x. So you see the functions switch. So 1 is above, e to the minus x squared is above e to the minus x from 0 to 1, and then it switches after 1. So we need to handle them separately. So in this first part, e to the minus x squared is the bigger one. So we use the integral from 0 to 1, e to the minus x squared dx. Now we can't calculate this directly, but we don't need to because we know that this already converges. Okay, it's a definite integral. There's no asymptotes or anything like that, so it converges. Now, on this other part, we have the integral from 1 to infinity of e to the minus x squared dx. Okay, so now we need to use the fact that e to the minus x is bigger. Because if we look here from this first part, we see that minus x squared is going to be greater than or equal to minus x. So e to the minus x squared is greater than or equal to e to the minus x. So this was from 0 to 1. But if we look at the other one, where x squared is greater than or equal to x, then minus x squared is less than or equal to minus x. So e to the minus x squared is less than or equal to e to the minus x. So that means e to the minus x is the upper bound in this case. Okay, so we can calculate this one instead. So the integral from 1 to infinity of e to the minus x dx, we saw that was e to the minus 1, which was less than infinity, so converges. So since the upper bound converges, the original also converges. Okay, which is what we wanted to show. So we use this upper bound function to show that the original also converges. Okay, any more questions on that? Okay, let's have a look at another example. Okay, example 2. We've got the integral from 1 to infinity of 1 plus e to the minus x over x. Okay, it's an improper integral. The upper bound is infinity. And we want to see if it is divergent. Okay, so I've got this integral here. Show that it is divergent using the comparison theorem. Okay, now you could just do it directly. Okay, you could integrate this directly and see what you get, but we want to try and make things simpler by using the comparison theorem. Okay, so note that 1 plus e to the minus x over x is greater than 1 over x. Okay, so it must be bigger because we are adding something extra to it. Okay, so since e to the minus x is always greater than 0, so e to the minus x is strictly positive, we know that adding it to the numerator must make it bigger. So if we remove it from this left-hand side expression so that the numerator just becomes 1, then the fraction must become smaller. So that's why this right-hand side must be smaller. Okay, are there any questions on this inequality? Okay, so we know that this right-hand side is smaller. So we've got a smaller function than our original function. So let's look back at our theorem here. So now we're looking at the second part over here, where g is the smaller function. So we've got a smaller function here, and we know that 1 over x diverges. So since the smaller function diverges, the integral with the smaller function, since that diverges, then the integral with the larger function, that must also diverge. So let's just show that. So the integral from 1 to infinity of 1 over x dx, that becomes the limit as t goes to infinity, integral from 1 to t, 1 over x dx. This becomes the limit as t goes to infinity of the natural log of x from 1 to infinity, from 1 to t. That's going to be the limit as t goes to infinity of the natural log of t, okay, because the natural log of 1 is just 0. And this thing goes off to infinity. In other words, it diverges. Okay. So we know that this smaller function, the 1 over x, it's a lower bound to our original function. That diverges, so the original must also diverge. So since the integral from 1 to infinity of 1 over x diverges, the original integral from 1 to infinity 1 plus e to the minus x over x dx also diverges. Okay, so again, we made use of the comparison theorem, but in this case, we wanted to show that something diverges instead of showing that it converges. Okay, are there any questions on this?
So can you go over it again?
Okay, sure. Okay, so just going over number 2 again. So we have the integral from 1 to infinity of 1 plus e to the minus x over x. And we need to show that this diverges. Using the comparison theorem. Okay, so we want to show that it diverges. So this is using the second part of the comparison theorem. Okay, this part B here. So we have our original function f. We need to find a simpler function g that is smaller than it. Okay, if we can find that function and we can show that that one diverges, then the original one also diverges. Okay, from the comparison theorem. So we need to find g of x such that g of x is less than or equal to 1 plus e to the minus x over x for all x greater than or equal to 1. Okay, so we want to make this simpler. So what we can do is we can just remove this e to the minus x. So removing e to the minus x from the numerator will make the fraction smaller. Because if we make the numerator smaller, then the whole fraction becomes smaller. So we've removed that. So we say, let g of x be equal to 1 over x. So we have removed e to the minus x, made the thing smaller. So that means this is going to be less than or equal to 1 plus e to the minus x over x. So here we've got our g being less than or equal to our f. We go back to our theorem. It says here g is less than or equal to f. If the integral with g diverges, then the integral with f diverges. So let's find the integral with g. So the integral from 1 to infinity g of x dx is equal to the integral from 1 to infinity 1 over x dx. Okay, so we need to write this as a limit. So this is going to be the limit as t goes to infinity, integral from 1 to t, 1 over x dx. This is going to be the limit as t goes to infinity, the natural log of x from 1 to t. Okay, that will be the limit as t goes to infinity, the natural log of t minus the natural log of 1. But the natural log of 1 is just 0, so that goes away. So we just left with the limit as t goes to infinity of the natural log of t, but this diverges. This goes to infinity. So the integral from 1 to infinity, g of x dx, diverges. So from our comparison theorem, it says that if this diverges, then the original also diverges. So this implies that the integral from 1 to infinity of 1 plus e to the minus x over x also diverges. Okay, which is what we wanted to show. Okay, let's have a look at some of the homework questions. Okay, number 1. Okay, let's say here, use the comparison theorem to determine if these integrals converge or diverge. Okay, we've got 6 to go through. So number 1, we have the integral from 0 to infinity of x over x cubed plus 1 dx. Number 2, we have the integral from 1 to infinity 1 plus sine squared of x over root x dx. Number 3, we have the integral from 1 to infinity of x plus 1 over the square root of x to the 4 plus x dx. Number 4, we have the integral from 0 to infinity of arctan of x over 2 plus e to the x dx. Number 5, we have the integral from 0 to 1 sec squared of x over x root x dx. And number 6, we have the integral from 0 to pi of sine squared x over root x dx. Okay, so we've got these 6 here. You need to use the comparison theorem to determine if the following converge or diverge. Okay, so 6 questions here. If you upload them to the class WhatsApp group, if it's correct and you're the first one to upload, then you'll get your bonus marks for the upcoming summative quiz or the test 3. Okay, so I'm using your bonus marks wherever they needed most. So if your summative quiz was really good, but your test 3 is not so good, then your bonus marks will go to your test. Okay, or if it's the opposite, I'll swap that around. Okay, are there any questions about these homework problems? Okay, so I'll post these to the WhatsApp group so you can have a look at them there as well. And then later today, I will upload all the solutions if you haven't done so already. Okay, but if you do have any questions on these, please let me know on the WhatsApp group or through email. Okay, and then I'll see you tomorrow for the new section on finding the lengths of curves. Okay, so there's going to be 2 lectures on that, and then we're going to do some test revision. Okay, if you do have any questions on anything we've covered, for the scope of test 3, then please ask for that as well. Okay, I'll see all of you tomorrow. Bye, everyone.